So last week we went through all these little things here, right? We went through all the definitions for distance and things in kinematics, right? Distance, displacement, speed, right? Velocity, acceleration, and so on, right? So we went through those definitions. We went through time graph. We looked at what the gradient of a displacement time graph gives you, what the gradient of velocity time graph gives you, and the area. Then we started to focus on Newton's laws of motion, right? We focus on Newton's law, right? And we have the three versions of Newton's law. Before Newton's law was Aristotle. Aristotle said that velocity was proportional to force, right? Those are Newton's three laws, and then we have the worded versions, of course. Then we spent a lot more time on something called momentum, and we said that linear momentum was the product of mass and velocity, and we said that momentum was what type of quantity, Aidan? Aidan? What type of quantity was momentum? Mathematics? A vector quantity, right? So direction important. And then we have collision, then we focus on conservation of momentum. What did conservation of momentum say, Vishesh? What did conservation of momentum say? Huh? What did conservation of momentum say? Huh? What was it? The total momentum before collision equals the total momentum after collision. All right. So that's basically what the law of conservation of momentum says. So if two objects collide, the momentum before equals the momentum after. All right. So we're going to continue now doing the same thing. So we're going to attempt past paper type questions now. Okay. All right. That's the best I can do there, earlier. That is the best I can do. Okay. We'll take a little read. Right? Draw a little diagram showing before and after, and see if you can answer what they want you to work out, right? If you can't see that, take a little picture and zoom in, right? Try that, please. Trolley A and trolley B, they collide head on. They give you the info about trolley A and info about trolley B. Right? Find the initial momentum, and then they will ask you something after, right? Oh, yeah. You have to draw that down, go right ahead. My name is Puneet. Huh? My name is Puneet. Yeah. Yeah, move it out there. Now that's all right. Still up all right. Please make sure you question a formula and a unit. Okay. But if I momentum again, scenario. But if I momentum again, mass by the velocity, right? Please pay attention to direction. I can move it down now, right? I can move down. Assuming that the trolleys are locked during collision and that they move off together in one direction, determine the speed and direction, right? The speed and direction of the joint trolleys immediately after. Right, so we'll be out for after now. Last 2 minutes.
Then
Ready? Ready? Alex, ready? Almost. I'm when you it. Hello, when you. Let us check on your first 2 parts. Right? I like to draw a diagram, right? You don't have to. So you have a trolley, right? One going west. So you have your first trolley here. Going west. Right? That is 72 kilograms. So you're going west, right? That's trolley A. Going west with a speed of 5.5 meters per second. And then you have trolley B, mass of 69.4, traveling with a speed of 4.5 this one. Right? Part one. Part one, they wanted to get part one, they wanted to get the initial momentum. So if you consider that momentum was positive, and the next will be negative, right? It's up to you, right? One negative, the next one will be positive. So the momentum of trolley A will be the mass of trolley A by the velocity of trolley A. So that'll be 72 by 5.5. How much is that? 312.3. SI unit, kg.
Oh, wait. Well, mine was minus 396.
How much?
396. Yeah.
396. Okay. And then part two, the momentum of B will be 69.4 by 4.5, which was that is what? 312.3 kgms minus 1, right? Don't leave that out there, right? And good. And because it's the opposite direction, I put a negative sign here, negative sign here. Okay. Then they said that they would stick up together, right? They would walk together with one velocity. So everything we've been doing was before. Now, let's assume after. I will assume we're going this way, right? So the combined mass of A and B will be 69.4 plus 72. So that combined mass is how much? 141.4 kilograms, right? That's the combined mass. Everybody okay? And they're moving up together. So we know that momentum before equals to momentum after. Right? So the momentum, so I write in the rule, I'm going to the top here, right? So I write in total momentum before collision, right? Don't leave all that up. Is equal to the total after collision. Right? Again, some trouble to write there. Right? So before collisions, before they collide, the momentum was 396 plus minus 312.3. And after they collide, it would have been 141.4 multiplied by V. Okay? So all we have to do now is to make V the subject of the formula. Right? So the last part is V is equal to something over 141.4. Right? That will be the 396 minus 312.3. How much is that? How much? Yeah, minus them and then divide by 141. And you get us 0.59? No? Negative? Well, yeah, it might be you may have gotten negative because your trolley A was in the negative direction. Correct? Check and see. Yeah, the sign of matter because they want to know what direction it's moving in. So it's 0.6. Yeah. Yes, it matters, right? Remember, if I choose going to the east as negative and west as positive. So if you switch it around, as west as negative and east as positive, then your final answer may have been negative. Right? So my final answer is 0.6 to the west. Okay? That's your final answer. So tell them 0.6 meters per second to the west. If you got negative, maybe you switch it around, right? Yeah. Right. Very good here. All the negative direction. No. But right, same thing. Because 0.5 and more, you're going to go west. Mine is the same thing. 0.6 going west, right? All right, online, so don't forget to write 0.6 meters per second going west. Right? Nice job, Richie. Good. Alia, you all got that? Right? So most important when you're doing questions like this is that you have to include the minus sign, right? Everybody okay with that? Yeah? Yeah? You done? You okay? Let's go again. Oh, we have a test again. Again and again. Oh, I really like this one. I like this one. This one is more a worded explanation, but you can use numbers to explain it, right? Big crash on the highway. See if what is saying be making sense. Try that, please. Two trucks, equal mass, same speed. All right, I will say anything. You read it. Because see, take a picture. Right, give them a worded explanation, but you can put a little diagram and they'll be able to see what's going on. Yeah. Thank you. Good night. We draw a little diagram, it might be able to show what's going on, right, Ada? So what's yours to say? Well, you do an explanation, huh? Diagram will help you explain. Back a minute. All right, so let's check this out here. So you have two trucks, right? The diagram does be perfect, right? So you have two trucks, mass. They both have the same mass going with the same speed in opposite directions, right? Like here, same mass, same speed, opposite directions. And they said that they both remain stationary on impact. Explain this crash in terms of the conservation of momentum, assuming the masses and the other contents of the truck are equal. Right. So first thing first, let's look at the scenario before. Right? Because by just looking at the scenario before, you'll be able to figure out after. Right? What's the momentum of the first truck? Based on the letters I use. Ethan, what would it be? So what would it be? M by V, right? Correct? Yes, M by V, right? What would be the momentum of the second truck? What would it be? Minus M by V. What would happen when you add M by V and minus M by V? You'll get 0. So what does that mean? It means that the total momentum before collision is 0, right? So what do you expect the total momentum after to be? 0 as well, right? So does this make sense? If the total momentum after collision is 0, then the object should be what? Stationary. That's okay? All right. So take this small thing down. The total momentum of the trucks, and of course the diagram here is going to help with your explanation, right? The total momentum of the trucks before collision, the total momentum of the trucks before they collide will be equal to 0. Will be equal to 0. Therefore, by the conservation of momentum, therefore, by the conservation of momentum, the total momentum after collision will also be 0. The total momentum after collision would be 0, will be 0. That full stop. Since they both were stationary after impact. Since they both were stationary after impact. Since they were both stationary after impact. This shows that the momentum. This shows that the momentum after collision is zero. This shows that the momentum after collision was zero, and hence momentum is conserved. Right? And hence momentum conserved. And hence momentum conserved. The second part of the question. To the second part, but try the first part. Another point. We can use small number, small calculations to show it. You can go ahead. One more after this, right? Finish already? Okay, now rest of. Done? Finished? Okay, thank you, right? Right, let's go. Right, first part, find linear momentum. Linear momentum is what? Ethan, what is linear momentum? Product of mass and velocity. That's all, right? One easy math there. State the law of conservation of linear momentum. You just write the law. When two or more bodies collide, total momentum before is equal to total momentum after collisions, provided no external forces act. Okay? Right. Now I want somebody to help me explain how it applies in the experiment above, right? Like click on Nathan. Try to explain part 2 from Nathan. How is momentum conserved in that example of curves? Sorry. In that example of curve. Huh? Why is Newton's third law to explain how it applies then? What's the conservation of momentum again? What is it? What's the conservation? Help him there, Aidan. What's the conservation? No, what's the conservation of momentum? Same thing that's right? Did you write it down? So come on, what it says? Just write it out there for part 2. I didn't write it. So I expect to know it. Tell me now. How many science are you using to learn it? Right? How come? How is the law? Tell me what is the law? The law is what? Total momentum before equal to total momentum after. So Vishish, what's the total momentum before those? What's the total momentum before collision? Huh? Okay, so we have 1 to say, right? But let's pretend each has a mass m. What's the momentum before collision? Each has a mass m. Because they all identical, right? What's the momentum before collision? Nathan, what are you doing? Should we try to listen to understand what's going on here? All right, so you can explain it. Huh? That's the total momentum before. Why is it? I'm not saying you're wrong, but why is it MV? Why is it MV alone? And it have 2 other objects here, B and C. So why is it just MV? Right, yeah, it is before, but why is it just MV? Because only one moving, right? The next 2, their momentum is 0. That's okay? Right? Now, Nathan, look at after collision. What's the momentum after collision? MV, why? Only one moving, these 2 here at rest. That's okay? So therefore, the momentum before equals to the momentum after. Okay? So all you have to say is that the momentum before collision is equal to mv, because only ball A is moving. Right? I do the same thing for after collision. Only ball C is moving, so the momentum is m by v. The momentums are equal, therefore, momentum is conserved. That's okay? That's all you have to do. Find momentum before, momentum after. That's okay? Serena, online, are you okay with that? Arissa, Maria? You're okay with the explanation there? Where we want to explain this part here. All right, nice. Yeah. Okay. Right. So here's the problem, part 3. I sort of gave you, I think I gave you an explanation when we were doing Newton's cradle, right? So I want to pick on why pick on the copy on it. What's the name again? Rajiv helped me out there now. And you were here last day? Yeah, you were right. You were here last day. Rajiv, so I need some help in the last one. In terms of forces, explain why ball A came to a rest, why ball B remained stationary, and of course, well, C move away. Which law are we using here? Newton's what? First, second, or third? Third. Right? Try it now. Try something. Why it is ball A came to a rest? So first question now you should ask yourself, is there a force acting on ball A? If something come to a rest, is there a net force acting on it? No. The net force has to be what? 0, right? All right, let's think about it. If we can do it, I'll have great. Part 3, the same question you asked Monday. So don't make a try, boy. Make a little try now. Part 3, you have to explain. Right. Why I think E came to rest? There's no force acting on it. No net force acting on it. Rima, can I hear your explanation? Why it is A came to rest and B remained stationary? B came stationary and well, C move on. Because according to Newton's third law, that's it.
If the action there is not equal, okay, but every action have like equal opposite reaction.
Cannot get full mark, it's 4 marks. All right,
Next, please.
All right, go ahead.
So the total momentum.
No momentum, just forces.
Force of A.
Everyone try? Yeah?
The force from the B and
So that cancel out on it, right? You're close there, let's miss one thing. Close there. You sure B move away?
C.
Right, and B remains stationary. So here's what happened, right? So watch it here, right? I will try to, let's try to put some numbers in there so that might make sense to some people, right? So imagine A exerting a force of 5 newtons on B. B will exert an equal and opposite 5 newtons on A. What will happen there? Cancel off, right? So A remains stationary. That's okay? Now remember, B was next to C. So now B is going to apply a force to C, 5 newtons again, and C will exert an equal opposite force on B. What will happen there? Cancel off, right? But anybody applying an equal and opposite force on C? Now, nobody applying an equal and opposite force on C. So C moves away because it has a force F acting on it, basically. Right? So technically, in a way, the 5 Newton force transferred from A all the way to C. That's okay? Are you okay with that? Well, they have that? Call it over again. Right? So write this down. Online, you're okay with the explanation? So basically, I have to state due to Newton's law. And you can't just stop your explanation by saying every action equal opposite reaction. Mike, what you will get for that? Mike, yeah, I'm asking. Nah, I don't ask. So you want to get your whole mark. Right? So object A, sorry, no, not object, and ball. Ball A exerts a force on ball B. and ball P exerts an equal and opposite force on ball A. Hence, ball A stays stationary. Hence, ball A becomes stationary. Full stop. Ball P exerts a force on ball C. And by Newton's third law, ball C, and by Newton's third law, ball C exerts an equal and opposite force on ball B. By Newton's third law, ball C exerts an equal and opposite force on ball B, keeping it stationary. Beat the B, beat the A, beat the C, C the B. That's all information. Hence, B remains stationary. Hence, B remains stationary. Question didn't ask, but full stop. C moves away. C moves away because there is no. C moves away because there is no equal and opposite force acting on it. C moves away because there is no equal and opposite force acting on it. All right, let's go back to something easy now with no explanation, more calculations that you're like. Just tell me the answer now. What's the SI? Sticker. It is the, hold on, Tell me the SI unit. Scenario, what's the SI unit for force? That's simple. What's the SI unit for force? Force is in Newtons, right? All of you, I know those things, right? What's the SI unit for linear momentum, smart? Nice. Okay. Newton's third law, something like the same. What's Newton's third law? That's it?
But every action there is an equal answer.
Okay. Right, let's do the calculation now. Quick ignore the first part. Just do the calculation and we're done. Just do the calculation and we finish, right? No, we finished that. 1 minute. Come in. Right, copy that down, try that please. Try that. So that's good. Then let's see online message answer, please. Let us see. Let us see. Let us see. Right, so let's see. Let's see what we get. See here. So we have an 8 kilogram moving east. That's 8 kilograms. East is 10 meters per second. And then what's the next one? 2 kilograms going with a 5. Right? And then after collision, find the final velocity of the boat. So they move together, they're always together. So they move up together. Right? So again, before you start doing it, you have to write total momentum before collisions is equal to total momentum after. Momentum before would be 8 by 10 plus 5 by minus 2 plus 2 by minus 5. Total momentum after will be what, 8 and 10 by V. So I have 80 minus 10 V. That's 70 divided by 10 is V. The final answer is 7. Positive 7. So it means that you're going to the east. Okay? Eastward, right? So the velocity is 7 meters per second eastward. Okay? Right? So that brings us to the end of momentum. Okay? Log on, test time, code time. Slash test. Push up. Anybody else write it? Sorry, they're online. Right? We have a little Kahoots. Based on everything that we did, I used these marks and adding up all these marks, right? I call them parents, that's some marks a little bit. Generate a report. Okay, everybody, that's it. certain people are talking. Right, you want an iPhone too? I'll tell you the downgrade a little. iPhone, you do something. You just call and talk to them and alright, log out there. I mean, talk to myself. Let's log out there. Log in. Right, let me see, let me look for this thing here. Where is it? Where are you? Where are you? Where are you? Where are you? You are here, you are here. Right, is it here? Kinematics 1 for the physics people. What's this for channel? Let's keep up something. Let us go, let us go. Right, log in there. Alright, log in. Logit, inet. This one fairly simple except for a couple of things, right? Ideally, you want to test yourself, go look back in book, right? That control, that one. What watching? Yes, watching. Well, you go ahead. Add that to your report. Alex always looking to cheat.
What?
Right, log in quick. Done it? Done it, log in there. You was there? Huh? What you oh, you got in school? Oh, okay. But I know I saw you there. I was not. That's what I was doing. All right, let's go now. That's all. Now we're gonna attack. Let's go. Kinematics, any major calculations, nothing too difficult. Then they can do it here. 199 divided by 2. Alright, let's go. That's not done after this, right? We have something to look after. It's after this. Wait, so long already?
I did correct now.
Next, there we go, there we go. Type your answer. Double points, okay, very nice. Oh, I like this one, I like this one, I like this. No SI unit, right? Let's type your value. That was good, that was really, really good. I think she did, yeah, so was it from? That was really good. Dominique, Chimi, let's see. Huh? And then know the area under the graph. Right? The gradient is acceleration. Oh, wait, you think that's changed there? A whole new force. A whole new force pop up there. Right? She should know, how come I? Next one. Spell it right, yeah? R. Huh? Yeah, that's right. That's right. Like I spell it wrong. I know when I come out. Right, so it's important to learn this spell, right, Claudia? Have some words that they will not give it right, yeah? If they spell it wrong. Some words that might help you, like Indonesia is one. Might help. Oh, I like this one, I like this one. I really like this one. Find the accelerator. Right? Why is the answer 0? Because the force is the resultant force is 0, right? If F is 0, E will be 0. Isaac, boy, Isaac, come up there. Lorena, Mishishu, close, Annalie, Anasinalia, Bandina, here. Now we just eat on up there. Ah, I'm gonna get it one wrong. We just use that formula for that 100 times for the evening already. I cannot believe some people get out. Alright, last one. Take all the time, I don't nick back, I don't know if you can read it, right? Take your time with this last one here. It came to rest with the same speed, yeah, 20 words. But it's just like the question that we did with the trucks. I want you to kind of come to that. So that down would be hard to see. Right? So that was minus 3, right? Opposite directions. Alright? Now you see who hold on for the win. Third place, Annalie. Lorraine hold on for Segway. Will she still hold on? Right, good job to see. Alright, nice job. Vandina and Isaac hold on for 4th and 5th. Alright, good. Okay, so that is your kinematics, right? We still have some things to do other than interested today. Right? Because if I tell you to do it for homework, you're not going to read it. Right? So let's read it together. And then we'll wrap up, right? Yeah, let's read it together. The next thing is something you would have done in like form 1 or 2, right? It's called energy. Okay. But before I do that, I think I asked you to do it for homework. More likely you didn't do it. The link between Newton's second law and momentum. Yes, I did. I asked you to look at that tomorrow. Right? I asked you to look for a link between right? I asked you to look for a link between kinetic and Newton's second law, F equal to ME and momentum. Anybody saw the link? How can I link these two? Because in some definitions for Newton's second law, they use momentum instead of saying force proportional to acceleration. They use a different definition. Scenario. Yeah? Anybody can link it? Anybody online can link it, Prima? I want to link two of them. Momentum and Newton's second law. How are we doing now? Anybody online can do it? Any ideas? Just again? Yes. Yes. So of force required. So for example, if this moving and I want to change the momentum of this, I can apply a force, huh? So how do we see that here? So watch this here. Right, Eden? Watch this here. F is equal to M, A is equal to V minus U all over T. Right? So force is equal to mass by acceleration. That makes sense? Yeah, and we know this formula for acceleration, right? Change in velocity in time. Now, if I were to multiply everything by mass, what do I end up with? MV, right? This is called your final momentum. This is called your initial momentum. Okay, right? And this should make sense, right? If I apply a force to an object that's moving with velocity u, what will happen? If I apply this force for some period of time, that object will move to a different speed, right? If I add a force, right, it should go a little bit faster. Because of that change in momentum, I know that a force being applied. Or I could say a force creates a change in momentum over a period of time. That makes sense? Yeah? So that's also what Newton's second law says. Newton's second law says that when a force is applied to an object that is moving, there's a resulting change in momentum. That's okay? So let's do my favor now. Add this in, please. Right? You can add this in as a further explanation for Newton's second law. Right, there's a reason I give it up. When you see it proved on Tuesday, Friday, you'll see like a special on top. Right? So basically, force is equal to change in momentum on time. Right? And then we have one more thing to look at today. Right? Something called energy. Right? You would have done that before. I remember conservation and energy. Types of energy. Okay, so right on the scores. Right, so that's just the link I wanted you all to see. Right, remember I showed you, and I showed you all real life examples of momentum, right? Like the rockets and the right? All right, so we just want to talk about a couple of things. No simulation. I'm gonna show you. All right, so last thing I got to look at is something called energy, right? Right? What do you need energy for, Alex? To get work done, right? So basically, energy and work done is the same thing, right? Vishish? We got to talk here, man. Well, again, the 2 hours, 6 of them. No, that's it. But how you play? How I organize that device there. All right. So the energy body possesses is defined as its ability to do work. So if they ask it to define energy, energy is ability to do work. Okay. Therefore, the more work it can do, the more energy it has. Note that the work done by an object, so to find what will work do? Right? Work will allow it to apply a force to an object, and that object should move, right? So technically, work done is the product of the force applied by the distance moved. Right? If you do more work, then you can move the object further. Okay? Or you have a larger force. Right? So note that the work done by an object is the product of the force acting on it by the distance moved. You'll understand why it is I ask for a special definition or a more specific definition for moments now. Moments is not force by distance. Right? Force by distance move is technically work done. Right? But moment is force by perpendicular distance from pivot. That's okay? So that's why I want you to learn to use that. Make sure you learn the definition for momentum, moment. Right? So work done is force by distance. Work done is SI unit in joules or Newton meter. Okay. I was just showing you there this is your derived unit. These are your derived units, and this is your base unit. If a question asks for the base unit, that's what you have to give them. Okay, you don't have to learn it, you have to learn how to get it. Okay, right? So the base unit for work is kgm squared s to the minus 2. The base and the derived are either of these. Right? But the more popular is in Joule, right? Right? Here we have all the different forms of energy, chemical energy, electrical, right? And so on, right? Can I have examples of a few of them? What's an example of something with chemical energy? Huh? Chemical energy. Yeah, but like those bonds are more like electrostatic bonds, like bonds between protons and positive and negative. So it's not chemical bonds so much. A chemical bond is like chemical energy, sorry, not bonds. Chemical energy is like what you have in fuel, right? Fuel provides chemical energy, right? What provides electrical energy? In a circuit, you're able to get electrical energy, right? But let's take a battery, for example. How does a battery supply electrical energy? It must have a source, right? It must have a source. What's the source of that electrical energy? The chemicals inside it, right? So a battery takes chemical energy that it has inside it and provides electrical energy. That's okay, right? Magnetic, you should know that. What about electromagnetic? What is something that provides electromagnetic energy? Electromagnetic. I tell us how I define that. What about thermal? That's just heat, right? Nuclear energy, right? You didn't do this yet, but nuclear energy comes from like a nuclear reactor, right? When they try to break down some of those energy given off, sometimes it's nuclear energy. Sound energy, you know about that. What's kinetic energy? Energy in motion. What is potential energy? Energy due to position, right? And what's elastic potential energy? Like a spring or like a rubber band, right? That has elastic potential energy. All right. Conservation of energy, right? This is the one conservation I should never forget, right? Conservation of energy states that energy can neither be created nor destroyed, but merely converted from one form to the next. For example, the battery converts electrical energy into, chemical energy into electrical energy. All right. Look, there are four more examples here. A radio takes electrical energy and gives you sound and thermal. If you cook on a gas stove, chemical energy is converted into thermal. Hydroelectric, right? It takes water to give you mechanical energy, moving water to give you mechanical, that will give you electrical. And make a mistake here. The nuclear power station, it takes nuclear energy and gives you thermal and what? Why do you use a nuclear power station? Why do you need it? To give you electrical energy, right? To give you electrical, right? So I made a little mistake here. So a nuclear power station takes nuclear energy and gives you thermal and electrical. Okay, so all those are examples of the conversion of energy. Everybody okay with that? Right? 3 examples of solar energy, three examples of alternate forms of energy: solar, wind, and geothermal. Right? So for your homework, I want what each one is. Right? What is solar energy, wind energy, geothermal? Right? And how we can harness it. I think let's try to harness it. Okay, so your homework, all I wanted to do for me is to give me a brief explanation on solar, wind, and geothermal, and any application of it in the Caribbean. Only in the Caribbean. Right? Who uses solar, who uses wind, who uses geothermal, and why? For example, a country like Trinidad, we wouldn't be able to handle geothermal, right? A country like some countries have problems harnessing wind. I want you to figure out why. Okay. All right. And last thing, what is kinetic energy and potential energy? Kinetic energy is energy an object has due to its motion. So if something moving, it has kinetic energy. Faster you move, bigger the kinetic. Kinetic energy is given by this nice little formula here. Write it down. Okay, I can open this handout. Kinetic energy is equal to half mv squared. Yeah, that's you. Don't take a picture, write it down, Sheila. Yeah, you see, you have the handout and you're taking a picture. Huh? No, you don't have to print it. You almost finish with it. Write it down. Write down kinetic energy is a half mv squared. As soon as I see a Friday, I'm going to ask you what is kinetic energy. Right? So kinetic energy basically has to do with an object's motion, right? Half mv squared. And potential energy has to do with its position above the Earth's surface, right? The higher you go, the bigger your potential energy. Potential energy is the mass of the object by gravity by density, right? Last question before you go goes to Eden. I like your hand up there. Yeah, Eden. Can an object have both kinetic and potential? Give me an example. No. You all agree? Can an object have both kinetic and potential? Yes, where? Right? Like if something falling. If something falling, it didn't hit the ground as yet, but falling, right? If something falling and it's about 5 meters above the ground, it has potential and it's moving, right? So it also has kinetic. Right? So an object can have all kinetic, all potential, or mixture both. Okay? All right. So next day we are going to focus on kinetic and potential energy. Right? And then we can practice on that. All right, so that is it for today.